Hello everyone, I'm Professor Harrison and welcome back to our module on regression analysis. Today we're going to be covering how to interpret the two numbers that define a regression line, the intercept and the slope. We're following Margot, a graduate student trying to reassemble a story her family buried. Today she's working through a problem in her coursework though. She's trying to fit a line to some housing data. She turns to the next problem in her coursework. Last time we drew a straight line through a cloud of data, and we said that that line really comes down to two numbers, an intercept and a slope. Now let's try and figure out what those two numbers actually mean. Margot's problem here is a pretty standard one. We have a set of houses, and for each house, we know its size in square feet, and we know what it's sold for. We want a line that relates the two, so the price is a function of the house size. Let's say we fit the line and it comes out to this. The predicted price equals $40,000 plus $150 times the size in square feet. So $40,000 is the intercept, and $150 is the slope. We'll take them out one at a time, and let's start with the slope, because the slope is actually the number that you care about most often. The slope tells you how much the predicted price changes when the house gets 1 square foot bigger. Here, that number is 150. So basically, every additional square foot adds about $150 to the predicted price of the house. One quick way that you can make sure you've gotten the interpretation right is to track the units. Price is measured in dollars, and size is measured in square feet. So the slope has to be in dollars per square foot. So the dollars is on top and the square feet are on the bottom. And that's a price per square foot, which is exactly what the slope is going to show us. And this is what makes the slope so useful in practice. Let's say you're pricing a listing and the house in front of you is 200 square feet bigger than a comparable house down the street. You would bump your estimate up by 200 times the 150, which ends up being $30,000. The slope hands you a rule that you can actually act on. It's as simple as that. Now, one thing to be careful about. When we say the predicted price, we mean the average price for houses of that size. We don't mean some exact guaranteed price, so two houses that are both 2,000 square feet are not going to sell for the same exact amount every single time. Think back to the scatter from last time. The actual sales bounce around the line. The line just gives you the average for a given size, and the individual houses end up being a little bit above or a little bit below it. So now let's look at the intercept, $40,000. By definition, the intercept is the predicted price when the size is 0. You set the square footage of the house to 0, and the line just hands you back beta 0. But here's the catch. A 0 square foot house doesn't exist, and we certainly have never had one anywhere in our data. So $40,000 really isn't a meaningful price for anything. It's just the spot where the line happens to cross the vertical axis. Reading the line all the way out at 0, far outside the range of the houses that we actually observed, is called extrapolation, and it's something that you generally want to be careful with. This part is worth sitting with for just a second, because the intercept is not always meaningless. Think about two different regressions side by side. In our housing model, a size of 0 is nonsense, so the intercept is sort of just a mathematical artifact. But now imagine you instead regress a factory's total monthly cost on the total number of units that it produces. There, 0 units is a perfectly real situation. The factory could just shut down for a month, and in that case, the intercept would be the fixed cost, and the rent, the salaries that you still have to pay even when you're making nothing at all. It's the same math in both cases, but the intercept is always the value when x is 0. Whether that number means anything in the real world depends entirely on whether 0 is a scenario that actually makes sense. A couple more quick things to explain about the slope. The sign tells you the direction. A positive slope means bigger houses cost more, which is exactly what we'd expect here. A negative slope would mean the opposite, and the magnitude tells you the strength. A market where every square foot is worth $150 is very different from one where every square foot is worth $400. And notice one last thing. Up until this point, we've just been taking the $40,000 and $150 as given. We've actually done that on purpose. Interpreting the intercept and slope works exactly the same no matter how the line was estimated. The actual machinery for computing those numbers, however, from the data is what we're going to go over in the next couple videos. Margot finishes the problem and files the technique away. She knows that when she turns back to her own data, she'll be able to read whatever the line of fit she has in the very same way, both the slope and the intercept. So that's how you interpret a simple regression line. Two numbers with two meanings. The slope is the expected change in the outcome for a 1 unit increase of the input, and it carries both a direction and a strength. The intercept is the expected value of the outcome when the input is 0, and that's only economically meaningful when 0 is actually something that can happen. The last thing to keep in mind is that expected here just means the average, It's not a guarantee for any single regression. In practice, it's very rare for data to exactly follow the line of best fit. But the good news is that the interpretation of the intercept and the slope will be the same regardless of how you end up deriving your line.